Welcome back. Today we're going to look at priority queues, which is a variant of sorting that generalizes the idea to provide more flexible data structure that we can use for all sorts of applications. To get started, we'll look at the API and some elementary implementations. So a week or so ago, we looked at collections in Java and the idea of elementary data structures where we insert and delete items, and then the data structures differ on the basis of which item we choose to delete. We looked at the pushdown stack where we removed the item that was most recently added, and the queue where we removed the item that was least recently added. And then we talked about randomized queue or a bag where we might remove a random or an arbitrary item. Today what we're going to talk about is called the priority queue. And for that, we insert items, but when it's time to remove, we consider the items to have a total order, and we want to remove the largest or the smallest item. So this little example, if we insert P, Q, and E, then when we do remove max, we want to get the Q out. If later we insert X, A, and M, then we remove max. The largest one in there is X. And we insert P, L, and E, and then after a while we remove max P. So that's our basic setup. That's what a definition of what a priority queue is. So the API will look very similar to our stack or queue API, with the difference that we want to have generic items that are comparable. So the Java language for that is in the class header. We say that our generic type, key, extends comparable of key. That just means that our keys must be comparable, and we must have a compare to method that will compare it to another key. Otherwise, we have a constructor, and actually for some applications it's convenient to have a constructor that takes an array of keys as argument. Then in an insert, that's put something in like push in a stack or enqueue in a queue. Then delete the maximum. I referred to delete the minimum just to avoid confusion. We have implementation, separate implementation, usually min PQ, where we delete the minimum. Then test is empty, and we also sometimes have extra method that just gives us the value of the largest key, and also size, which is useful sometimes in collections. You might also want it to be iterable, but we'll skip that for now. There's lots and lots of applications of priority queues. Even though it emerged as a data structure relatively late in the game, now that we see that there are many algorithms that are much easier to implement when we think about the priority queue abstraction. We have data that we're processing. We can't process it all at once. We have to save it some way. And then what the priority queue tells us is let's organize it in some way so that we're always taking the best one to process next. And that turns out to be very close to a generic algorithmic design technique that we'll be looking at in many, many different applications. Today we're going to talk about event-driven simulation, which is an interesting idea that is based on priority queues, but it's also used in numerical computation, and we'll see in the algorithms for data compression and graph searching that it's useful, and in many other applications in computer science and in scientific computing. It generalizes the stack in the queue and gives us a data structure that we can use to effectively design algorithms of all sorts. So here's just a particular client that will help explain the idea. So our challenge is, let's say this is on the web. We have billions of transactions, and where they're streaming through our data warehouse or our processor in some way. And just a very, very huge number of transactions. In fact, we couldn't possibly hope to even store them all. There's trillions of them. They're coming through as fast as possible. But we're interested in the biggest ones. So maybe it's the biggest amount of dollars or the biggest cost or whatever it might happen to be. And so we can pick some number that we can store. We'd like to store the 1,000 biggest ones. So you can imagine a credit card company looking for fraud is going to care about keeping track of the largest transactions. So maybe we can store millions or thousands of them. So that's our parameter M. That's the number we can afford to store. But the total number of items, we couldn't possibly afford to store them. So, and this is just some test data where we've got all these transactions. And so we're going to be able to take in data like this, and again, an unbounded stream of data. But let's say we want to keep track of the top 5 values using the third column as the value. So we're going to look at a client program called top M that takes a command line argument, how many, in this case it's going to say 5, and then it's going to take from standard input the transactions, and it'll print out the top 5. So that's a canonical example of a priority queue client. We need to design a program that can do that. So with the priority queue abstraction, that's not too difficult to do. So we're going to use a min-oriented priority queue, so that's going to keep, it'll be one where we can delete the minimum. And it'll be generic, so we have a transaction type that holds this information, including natural ordering, where it's ordered by dollars, that last column. So we'll build a new priority queue, min priority queue, where we have the capability to delete the minimum. Then we read from standard input. We read a line, build a transaction from the information on that line, and that'll fill in the fields. And then we put that transaction on the priority queue. Now, if the priority queue has more than M items because we inserted that one, then we want to delete the smallest one there. And that way, we're keeping track of the largest M. Whenever we get a new one, then we throw away the smallest one that's there. So even with this huge stream of items coming through, we're only keeping track of the M largest item, and that's a fine canonical client for a priority queue. Now, how are we going to implement or solve this problem? Well, you can think of lots of ways to go ahead and solve this problem of finding the largest M items in a stream of N items. So, for example, you could sort them and then just look at the M at the end. But by setting up the problem, I already kind of ruled that one out because we don't have the space to sort them all, to store them all. So sort is out of the question. We'll look at a couple of elementary priority queue implementations that are straightforward. Keep the items like we would in a stack, and then when we need to find the smallest or the largest, look at them all. But that's going to be too slow. M is large and N is huge, and M times N is going to be too slow. What we'll look at is a very simple and practical implementation using a data structure called the binary heap that gets the job done in time proportional to N log M in only M space. And that's pretty close to the best that we could do in theory, and is a very important and useful practical implementation and data structure. All right, so here's just a overview of 2 elementary implementations for priority queues using the example operations that I gave before. So you can imagine keeping the items, say, in a linked list or in a doubling array, and just keeping just unordered, just as we would in a stack, just keeping them the way that they come in. We put a new item at the end of the array and remove it from the end of the array, or you could do it in a linked list. And then when it's time to remove the maximum, you have to scan through everything to find the maximum. So that's one way. You could implement this with a linked list or with a resizing array. Or you might decide, well, let's try to keep things in order, and then that might involve some work. It's like insertion sort. You have to find the place to put the new item and then put it in the right place. And again, you could do this with a linked list or with a resizing array, but then with array, you'd have to move all the larger ones over one position to fit the new item in. When we insert E, and they're supposed to keep them in order, we have to move over L, M, P, and P to get the E in, and so forth. But the advantage of that might be that removing the maximum is easy. We just take away the one at the end. To remove the Q, we know it's at the end. To remove the max at this point, that's X, it's right at the end, and P is right at the end. So you can imagine the implementations of priority queues using these two basic strategies. Not much code involved. This is a unordered array implementation of priority queues. And it's quite straightforward. We didn't put in the, this is the cheat version where we require the client to provide a capacity, but we could easily change this to a resizing array. So insert just puts it at the end, and since it's unordered, delete maximum has to go through the entire array to try to find the maximum. When it finds it, it exchanges it with the one at the end and then removes it the same way that we would in a stack. And it'll use less in exchange just like we would in sorting methods. So that's a fine implementation if the priority queue is going to be tiny all the time. So if you, without even implementing it, you can understand this table that if we use an unordered array implementation, we can get insertion done in constant time, but we have to look at everything to delete the maximum or even find the maximum. If we keep it in order, we can find the maximum or delete it in constant time, but it takes us linear time to insert. And since, as with stack and queue operations, these insert and deletes might be intermixed in arbitrary ways, and there might be huge numbers of them, neither one of these is very attractive because they're going to take n times the number of operations. Whereas what we can hope for and what we actually will achieve is to get log n time for all operations, time proportional to log n for all operations. With a clever data structure and interesting implementation, we can actually achieve that goal. That's the basic API and some elementary implementations for priority queues. Now we're going to look at binary heaps, which is an ingenious and very simple data structure that's going to help us implement all the priority queue operations quickly. So the idea of a binary heap is based on the idea of a complete binary tree. So a complete binary tree, well, first of all, a binary tree is either empty or it's a node with links to left and right binary trees. So that's an example of a binary tree. A complete binary tree is one that's perfectly balanced except possibly for the bottom level. So there might be a few nodes on the bottom level and one level lower than the bottom level, but otherwise all the levels are full. And we'll see how that looks in just a second. The property of a complete tree is that the height of a complete tree with n nodes is the biggest integer less than log base 2 of n. And that's really easy to convince yourself that that's true because the height, if we add nodes one at a time, going from left to right on the bottom level, say, the height only increases when n is a power of 2. Complete binary trees actually happen in nature. Here's an example of one that goes 1, 2, 3, 4 levels at least. So 16 bushes at the end there. All right, now the way we're going to use complete binary trees to implement priority queues is to, first of all, associate information with each node. We'll put our keys in the nodes. And also, we're going to represent it with an array. So when we start putting the keys in the nodes, we're going to impose one more condition that's called heap ordering. And the idea is that the parent's key is going to be no smaller than its children's key, and that's true for every node in the tree. The array representation, all we do is we start with indices at 1. It's a little less calculation that way. We leave A of 0 empty. And then we just take the nodes in level order. So first we put the root, then we put the 2 nodes on the first level going left from right, and then all the nodes on the third level going from left to right, and so forth. This is interesting because we can draw the tree to get more intuition about what's happening, but in the actual data structure representation, we don't need any links at all. It's just an array. The way that we move around the tree is by doing arithmetic on the indices. So let's look at a few properties of binary heaps. So that's complete binary trees represented in an array with keys in the nodes satisfying the heap order property. Well, first thing is that A of 1 is the largest key. It's larger than the keys. There's 2 children and they're larger than theirs and so forth. So it's the largest key in the data structure. The other thing is, as I just mentioned, you can use the array indices to move through the tree. For example, if the node is at position k, index k in the array, then its parent is at k over 2, and that's integer divide. So the parents of, say, h and g are both n. H is at 10, g is at 11, n's at 5. So both of those are 10 over 2, 11 over 2, integer divide is 5. And going the other way, it's easy to see that the children of the node at k are 2k and 2k plus 1. So we don't need explicit links at all to represent these data structures. We can just use array indices. So that's the basic setup or the invariant that we want to maintain in this data structure. And now what we're going to do is take a look at just a couple of different scenarios that where we violate that invariant temporarily and then fix it. And that's going to give us the flexibility that we need to implement priority queue operations. So one scenario shown here is if for whatever reason a child's key becomes larger than its parent's key. So in this case, we have an example where T, the node T here, its value changes and it becomes larger than its parent key P. So the heap order condition is satisfied everywhere except at this node. Well, it's easy to fix this one. All we do is exchange the key in the child with the key in the parent. After that exchange, then that would have T up here and P down here, then the heap order condition is satisfied at that node because the parent was smaller, so that one's smaller. And this other one is still smaller, so T is, after it's exchanged up here, will be bigger than both its children. But the heap condition will be violated because T is still smaller than S. So we have to do it again, exchange it with S. So we move up the tree, exchanging the larger key with its smaller parent until we get to a point where it's larger than both its children. That's restoring the heap order along a path from the place where it's violated to the root. You can think of that as kind of like the well-known Peter principle, where a node gets promoted to a level where it finally can't be better than its boss. It's a level of its maximum incompetence. And implementing that in code is really easy. We call that the swim operation. It swims up to the top. And if we have a node at index k and we know the heap condition is violated there, as long as we're not at the root and k's parent, k over 2, is less than a of k, then we just exchange it with its parent and move up. That's the swim operation to eliminate a violation when a key value increases. So, for example, this gives us a way to insert a new element into a heap. What we do is we add a new node at the end of the heap. So that's one position over. The thing is, remember, represented in array, 1, 2, 3, and so forth. So the next empty position in the array, there's a place to put a new node. And then we just declare that that's part of the heap. And that node, well, if it's less than its parent, we're fine. But in general, we have to check whether the heap condition is violated and exchange it with its parent as long as it's smaller. And that's just perform the swim operation. So if n is the number of items in the heap, defined to be in the heap, we're going to increment it, store our new key there, and then perform the swim operation. So that's a quick implementation of the insert operation. And notice, since it's just going from bottom to top in the heap, it takes at most 1 plus log base 2 of n compares. Now there's another scenario where a key becomes smaller. For whatever reason, a parent key decreases, it might become smaller than one or both of its children's. In this case, the value at position 2 is changed to h for whatever reason, and that's smaller in this case than both its children. So how do we fix that violation? Well, that one's also easy. We figure out which of the children is larger. In this case, it's the s, and we exchange that one with the one that's violating the condition. So that's moving the smaller key down. After that exchange, then S is in position 2, and it's bigger than both P and H, and the heap condition is only violated, again, where H is sitting. And again, we keep going until getting to the bottom or getting to a place where both children are smaller. And that's maybe a little bit what happens when a new boss is hired from the outside. And then the two subordinates struggle to take over that position, and then the boss would get demoted to its level of competence. And again, that level of flexibility, here's the implementation of it. And again, it's quite straightforward, using the index arithmetic to move around in the heap. And that's called the sync operation because we're going down in the heap. If we're at position k, then what we need to worry about is the nodes at 2k and 2k plus 1. And the first thing to check is find out which one's bigger. It's either 2k or 2k plus 1, and so set j accordingly. So that's j now, is after this statement, is the larger of the two children. And don't forget to check that we're going off the end of the heap. And then if the k is not less than either one of those, then we're done. If it is, then we exchange with the larger of the two children and move down the heap. Again, just a few lines of code to eliminate the violation when a key value in a heap decreases. And that one we're going to use to implement delete the maximum in a heap. So delete the maximum, we have to do two things. One thing is the size of the heap has got to go down by 1. The other thing is return the maximum. Well, we know the one that we want to return is the one at the root, so we'll save that value away to return to the client. And then, since it has to go down by 1, the place to get remove the element from the heap is at the end of the array, because it's now going to have to not occupy that position. So we take that element and replace the root with it. So move the h up, and actually put the root value there, just exchange them, but it's no longer in the heap. Now, that element, which went from the bottom to the top, is most likely going to violate the heap order. It's going to be smaller than both of its children, so we do a sync. Now, in this case, to implement delete max, we save away that value at the root in max, and we eliminate loitering by nulling out that vacated position, then return the max value. So that's an implementation of the delete max operation for a heap using sync, where a key value that decreases goes down in the heap. So let's just take a look at what happens with a real heap with the demo when we do these things. And you'll have a good feeling for how this data structure works. So we're starting at some point where we have these 10 keys in a heap, and it's heap ordered. So we've drawn the data structure with the links, so we have an intuition for what's going on. But all the program sees is the array in gray at the bottom, where T's in position 1, P and R position 2 and 3, and so forth. So now suppose that we're supposed to add S. So to add it to the heap, that's going to go in the position at the end. And then now we've added it to the heap by just incrementing n and putting it in there. But now we have to bring the heap order back into condition. And so that's going to, that key is larger than its parent, so we're going to swim it up, exchange it with its parent as long as it's smaller than its parent. So first thing it goes up to exchange with the S, it's still bigger than P, so we exchange it with the P. And now we're done because S is not bigger than T, and the heap order condition is now satisfied everywhere in the heap. So with just 2 exchanges, we insert that new element into the heap in this case. Now suppose the next operation is remove the maximum. So we're going to take T and we're going to exchange it with the last element, and then declare that to be no longer part of the heap. So now we have to bring the heap order back because it might be violated at the root. So now we invoke the sync where we exchange that node with the larger of its 2 children until we find a place where it's larger than both its children. So S is the larger of the 2 children R and S, and now H is still smaller than both its children, so we promote the larger, which is P. Now H has no right child, just a left child, and it's larger than that one, so we're finished with that operation. We've removed the maximum, and we still have our data structure heap ordered and our n keys stored in the first n positions in the array. Let's remove the maximum again. Again, we take it out by exchanging, this time G with the root, and then decrease the size of the heap by 1, just take that out. Now the node at the root violates the heap order, so we have to exchange it with the largest of its 2 children. In this case, that's R. Again, G is not larger than its 2 children, so we have to exchange it with the larger of the 2, that's O. And now we're done, we've removed the largest again. Now suppose we insert S back into the heap. So that's adding it at the end, violates the heap order, exchange it with the parent who's smaller, and keep doing until we get to a place where it's larger than its 2 children. In this case, S goes all the way up to the root, and it's all heap ordered again. So that's a little survey of some operations on a heap, and you can see how every operation is done with just a few exchanges along the path from the bottom to the top, or the top to the bottom. Okay, here's the complete Java implementation of a priority queue using the binary heap data structure. It's actually not so different from the elementary implementations that we looked at in the last section. Our representation is an array of keys and a size. That's the number of items in the heap. For simplicity, we'll show the code where the client gives the capacity of the heap. We can use a resizing array in an industrial strength implementation, the same that we did for stacks and other data structures where we use arrays. So we'll build a new array of keys, and we have to use an ugly cast because we can't have generic arrays in Java. And that's so it's comparable, and we need one more than the capacity to handle this thing where we don't use position 0. So the priority queue operations is the insert and del max that we just showed in the previous slides. Isent is just checking whether n is equal to 0. We have the swim and sync functions that we showed earlier, and then we have helper functions less and exchange that access the array directly so that the code doesn't have to access them directly. That's a complete implementation of priority queues in Java. And this implementation by itself is extremely significant because it's really very simple, optimal representation of the data, and only a little arithmetic with array indices. But as you can see by looking at this table, it gives us a way to implement priority queues where both operations are guaranteed to happen in log n time. Now, experts have worked to come up with improvements on this, and there are slight improvements possible. We can make the heap D-way rather than just two-way, and depending on the frequency of execution of the insert and del max operations, that might work out better. There's an advanced data structure called a Fibonacci heap, where inserts are done in constant time and delete max done in log n time on average over all the operations. But that one's generally too complicated to use in practice. But still, again, using theory as a guide, maybe there's a way to, to decrease costs a little bit from binary heaps. And of course, we cannot get down to having constant time for all operations. Why? Well, we can sort with a heap by inserting all the elements and then deleting the maximum and getting a sort done. And that would be linear time if we had this kind of variation, if we had constant time operations for both insert and del max. But for certain applications, we can get close to constant time for one or the other operations, and that'll be useful in different implementations. Now, there's an important consideration that we have to bring up related to the programming language, and this is a more general consideration than usually we bring into focus in algorithms, but it's worthwhile mentioning. We're assuming that the client doesn't get to change the keys while they're on the priority queue. And it's better not to assume that. It's better to arrange for that in our implementations by using keys that are immutable, whose values don't change. There's many reasons that immutable keys that programming languages provide the capability to build immutable keys, and this is a fine example of one. And we'll talk more about that in a minute. The other things that we didn't talk about in the implementation should throw an exception if the client tries to delete from an empty priority queue. And we should have a no argument constructor and use a resizing array to account for gradual growth and shrinkage in an industrial strength implementation. Usually we provide two implementations, one that's max-oriented, one that's min-oriented, so that nobody gets confused, and they're the same except less and greater are switched. We'll see later on, there's times when we want to expand the API and provide other operations like removing an arbitrary item from the priority queue, or give the client in the API the capability of changing the priority of an item. Our sink and swim methods are good for making this happen, but we'll delay these implementations until we need them in a more complicated algorithm. So what about immutability? In everything in Java is implemented as a data type, a set of values and operations on those values. And the idea of immutable data type is you can't change the value once it's created. So that's kind of like when you when you create a literal value to be assigned to an integer, it has that value. Here's an example, say using the a data type for vectors. It might be a way to implement vectors. So we put the word final to means that the instance methods can't be overridden, and not only that, instance variables are private, they can't be seen from the outside, and they don't change. And so a constructor for an immutable vector data type, it might take an array as its argument, and that array has got values stored in it, say of doubles, and those can change. But what an immutable implementation would do would be to copy those values into the local data array instance variable. And then those values are not going to change. And the instance methods won't change them, and the client can't change them. So that value stays the same. Lots of implementations, data type implementations in Java are immutable, like string is immutable. When you create a string, that value doesn't change. If you want a new string, you have to create a new string using concatenation or some other operation. And the same with the wrapper types like integer and double or color and lots of things. Whereas, on the other hand, sometimes the whole purpose of a data type is to maintain a changing value. Like a good example is a counter or a stack. So you wouldn't put those things on a priority queue because the value is changing, but the other ones you would. The advantages of immutability, and again, maybe this isn't the place to really sell those advantages, it's more for a programming language course, is that it really simplifies debugging. We can have more confidence that our priority queue operations are going to work correctly if we know that the type of data that's on the priority queue is immutable. If the client could change the values, how do we know that the heap order operation is preserved? If we want the client to be able to change the values, we're going to provide methods for that purpose, as I just mentioned. And there's many other reasons that people use immutable data types. There is a disadvantage that you have to create a new object for every data type value, but for a lot of applications that disadvantage is not viewed to be significant compared to the advantages. Here's a quote from one of Java's architect, Josh Block. Classes should be immutable unless there's a very good reason to make them mutable. If a class cannot be made immutable, you should still limit its mutability as much as possible. And many programmers live by that kind of precept. So that's a basic implementation of priority queues using the heap data structure represented as an array. Next, we're going to look at the use of the binary heap data structure to implement a clever sorting algorithm known as Heapsort. So here's the basic plan. What we're going to do is we have our n keys, and we'll have them in an array. We'll view that array as eventually being a max heap. So what we have to do first is to rearrange the keys in the array to heap order it. So just make it so that every key is larger than its two children. And for example, the largest of all the keys is at the root. And then the next phase would be to take that heap ordered array and get it to be a sorted result in place. And again, the heap is stored in the array with the first key position 1, next to position 2 and 3, and like that. So the end result would be like that with no keys in the heap, but all the keys in the array in sorted order. So it's a little exercise in abstraction. Part of the array is the heap, part of the array is the sorted subarray, and eventually we bring it down to the whole thing being sorted. There's very little code beyond the basic heap code that we've looked at can get this implemented. That's called Heapsort. Let's take a demo of how Heapsort works in our example. The idea is we're going to use a bottom-up method. So all that means is we start with an array in arbitrary order, and then we're going to work from the bottom up to make sure that it's heap ordered. Well, all the nodes with no children are heap ordered. They're only of size 1. The first one we have to worry about is this one here. The root we haven't examined yet. Its children are heap ordered, so it's a small heap of size 3 that may not be heap ordered. In this case, it's not because one of the children is larger. So that's where things are going to start. We have a lot of one-node heaps. And then we're going to have to perform the sync operation on this one at node 5. That's, in this case, just exchange it with this parent. And then proceeding in that way, moving bottom up or moving from right to left, the next thing we do is, then we have a 3-node heap that's heap ordered, and we're fine. Now we'll move over to the T, and again, that's the root of a 3-node heap that's heap ordered except at the root. We may need to fix it with the sync operation. In this case, nothing is required because it's larger than its children, so we have a 3-node heap. And then we move one more to the left. Now we're looking at the R. Again, root of a 3-node heap may or may not be heap bordered. We do have to do the sync operation. In this case, that brings the X up. 3-node heap. Now we go to 2. Now that's the root of a 7-node heap. We know the 2 3-node heaps that are children are heap bordered, but we may have to correct the heap ordering at the root, so we do a sync on 2. And that's going to involve exchanging with the T, because T is larger than O, and exchanging with the P, because P is larger than O. Now that heap is a 7-node heap that's all heap ordered. And then the last thing is to do the root of the whole thing. And again, now the 2 subtrees are heap ordered. That's what we mean by bottom up. We took care of the heap ordering from the bottom up. And so we'll do a sync on the S and bring it into heap ordering. So that's with just a few exchanges, we got that whole array heap ordered. And now what we want to do is take advantage of the heap ordering in the array to do a sort. And the concept is very simple. Right away, we have the maximum element in the array right at the root. We want that to be at the end, so that's what we're going to do, is just put it at the end. We exchange the element at the root with the last element, pull it off the heap, and then that's our example. We might have violated the heap order condition at the heap right now, so now we have to do a sync operation on the E. And so it's larger than it's both children, and the larger of the 2 children is T, so we promote the T. And the P is larger of the 2 children, we promote that. And then finally the E comes down to the bottom. So now that's one step in the sort. We got the largest element off. Now the next largest element in the array is now at the root of the heap. So we're going to do the same thing, exchange it with the last element in the heap. Then now the T is in its final position in the sorted array. We take it off the heap. So now we've got a heap with 9 elements, and 2 of the elements in the array are already in their final position. And now this one's not heap ordered, so we have to exchange it with the largest of its 2 children. In this case, that involves promoting the S and the R. Now it's heap ordered. So that's the end of 2 steps in heap sort. And then we just keep going, pulling off the largest element from the heap, exchanging it with the element in the heap in the largest position in the array, which brings that element into its final position in the sorted array, and then adjusting the heap ordering with the sync operation. So that E again is going to come down, and now it only goes down 1 step in this case. So now R exchanges with M, and it's in its final position. And you can see down at the bottom the large elements in the array filling in their final position. In the left part of the array is representing the heap. The R goes off the heap, do the sync operation on the M, and now we have a heap ordered array. So now do the P, exchange that with the A, take it off the heap, do the sync operation on the A. Now we're going to do the O, exchange that with the E, take it off the heap, do the sync operation on E, which involves promoting the larger of its 2 children until it gets to the bottom, or a place where it's larger than both its children. So now we have just 5 elements left. We'll get the M, do heap ordering on the heap of 4, and that only involves 1 exchange. Now we get the L. A exchange with the larger of its 2 children. Well, they're both the same, so it goes with the left one. That's a heap of size 3. Pull off the first E. It's already heap ordered. Pull off that E. And now we're left with only 1 element in the heap, and it's in the first position, so there's nothing to do. So with a series of N exchange and then sync operations, we pull the sorted array out of the heap. Okay, this slide summarizes the code for heap construction, and as you can see, it's a one-liner. We go backwards through the heap, starting at n over 2, because the n over half of the rightmost half of the array is just little heaps of size 1. We just go backwards doing a sync starting at K. So that's the first piece of code for heap ordering an array with arbitrary values. And then these diagrams summarize the sync calls that we just went through in the demo, starting at 5, 4, 3, 2, 1. As you can see, only 1, 2, 3, 4, 5 exchanges are needed to bring this into heap ordering. Then the second pass, again, that's only a two-liner. We exchange the first element with the one at the end and then decrement the size of the heap and then do sync operations. And these diagrams summarize the sync operations that we showed in the demo. On an ever smaller heap, we continue just performing sync operations at the root until we get a completely sorted array. Given the sync implementation, we had a one-liner for the first pass and a three-liner for the second pass. So that gives a complete implementation of Heapsort with the code that we've given so far. There's one little detail. When you're sorting an array, of course, position 0 comes into account. And we've been building our heaps from position 1, but we can take care of that in the less and exchange methods by just decrementing the indices in those methods to have it work as if the array were 0 through n. And that's a little implementation detail. But otherwise, this is a fine sort implementation that actually is very little code. And it's got a place in the theory of algorithms that I'll talk about in just a second. This is just another trace without the data structures shown to just show in our standard way the elements in black and red are the ones that are touched and the elements in gray are the ones that are not touched at all. And to just show that this thing gets the sort done with touching relatively few elements. That's a trace. Let's look at an animation. Animation of Heapsort is interesting to watch. The construction of the heap happens in a blink, and now it's pulling off the largest elements moving from right to left. So again, a very efficient way to get a sorting job done. So what about the mathematical analysis? Mathematical analysis for the heap sort part is pretty easy. N times, we're doing a sync operation, and the size of the heap is at most log n, so it's n log n. The construction actually, it turns out, although it's a little more complicated to prove, that it always uses just a linear number of compares and exchanges. And that's an interesting result in itself. You can build a heap from n values in linear time. And then in n log n more time, you can sort from that heap. And that's significant because it's the first sorting algorithm that we've seen that is both in place and manages to get the sorting job done with guaranteed n log n compares. Merge sort doesn't do that. It takes linear extra space. Quicksort doesn't do that. It takes quadratic time in the worst case, even though we make that unlikely by random shuffling. It still takes quadratic time in the worst case. But Heapsort does both. Now there's more complicated versions of merge sort and quicksort that can do this in theory, but Heapsort is a pretty simple algorithm that gets both done. So if on a job interview somebody asks you what's an in-place sorting algorithm that's guaranteed n log n, your answer is going to be Heapsort. Now in practice, Heapsort's actually not used that much for a couple of reasons, and they might ask you these on your job interview too. First thing is the inner loop is longer than quicksorts. Like merge sort, there's more things to do in the inner loop. There's that compare the two children bigger, and then compare. So there's two compares that get done in n log n times, and then there's some that array index arithmetic. The other thing, which is probably more significant on modern machines, is that the references to memory are all over the place when it's a huge array. So it's not a good algorithm for a situation where there's caching, which is almost everywhere nowadays. It doesn't have local memory reference like Quicksort does. It's always referring to something that's nearby something else that it just referred to. So if a big block of things comes into memory, there's no more extra cost. Whereas Heapsort is going to look far away from the current place as it goes down the tree, and that makes it slower in a lot of situations. And the other thing is it's not stable. Sometimes people choose to use merge sort in practice because of the stability, but Heapsort's not stable for the usual reason that it does long distance exchanges that might bring items that have equal keys back out of order. So that's our full summary of sorting algorithms. It completes our treatment of sorting algorithms with Heapsort. And this is just adding the Heapsort line to the table. It's in place. We don't use any auxiliary array. It's not stable, but its worst case guaranteed time is proportional to n log n, as well as the average and the best. This is not a trivial result, but it's also the case. So it's n log n guarantee in place, but it's not stable, and we still have the hope that someday somebody will develop a simple, in-place, stable, worst-case n log n algorithm, but we're not quite there yet. And that completes our treatment of sorting algorithms with the Heapsort algorithm. Now we'll look at an interesting application of priority queues that's actually representative of a whole family of critically important applications in applications of computing. It's called event-driven simulation. And the idea is we want to study some property of the natural world by simulating it. And that's something that's very, very common in scientific inquiry nowadays. And this is a very natural idea. And actually, the idea goes back to Einstein. So we want to simulate the motion of n moving particles that might collide. With a priority, this kind of simulation is enabled by priority queues. Without something like priority queues, you couldn't do this for a large number of particles because it would require quadratic time and simply can't be afforded for a huge number of particles. So let's take a look at how we can possibly make this happen. So we use a simple scientific model called the hard disk model, and then this is just for simplicity to get this done in just part of a lecture. Clearly, these things can be extended in many ways. So we're going to have moving particles that either collide with each other and with the walls, and each particle is a disk that's got known position, velocity, mass, and radius. And there's no other forces involved. It gets more complicated if there's more forces, like gravity involved. And this one by itself is very significant. As I mentioned, goes back to study of physics with trying to understand pressure and temperature and Einstein's famous experiment on pollen grains showing that their motion was Brownian or random. So whether it's individual atoms and molecules or it's some bigger kinds of particles, it's a complex dynamic situation that is better understood through computer simulation. And nowadays, that means priority queues. So as a warm-up, here's the code to implement bouncing balls without the collisions. And this is an elementary programming exercise that is the code at the left has the effect shown at the right. So we have a data type called ball that represents just one of the particles and has instance variables that has the position and the velocity. So we make a bunch of them, and then we have a while loop, which is just every 50 milliseconds, clear the whole drawing, and then move the balls a little bit, and then draw them in their current position. And the only thing the move operation does is to update the position of the ball by the velocity, which is just another number, and then it does the bouncing off the walls. If it happens to hit the left wall, you reflect the x-coordinate, and the right wall, you reflect the x-coordinate, bottom and top. You do the same for the y-coordinates. So this is an easy programming exercise given the right display primitives. And it's a good exercise in object-oriented programming, showing how just one implementation, then we can use that same implementation to simulate a number of instances. So that's our starting point in terms of the code. So this is the implementation of the ball class. So it's got position and velocity, as I mentioned, and every ball has a radius. And then there's a constructor, and maybe we have a constructor that takes arguments that would initialize the position and the velocity, or maybe initialize them to a random position if there's no arguments. And then here's the move method. And the move method, again, most of the times just takes the x and y coordinates and adds the current velocity times the speed constant, dt, or speed variable that's given as argument dt. And then these tests are for whether it hits the walls, in which case you have to flip the x or y velocity. And then draw is just using standard draw, just draw the ball. So that's all the code for doing the bouncing ball simulation. Now, what's missing in this is what happens when the balls collide with each other. And to cope with that, we need to do both a little bit of high school physics and a little bit of basic computer science. So the physics problem is exactly what happens when two balls hit. They bounce off each other according to some well understood physical process, and that's the high school physics. And the CS problem is how and when do we exactly do these computations for each of the balls, and how can we do it efficiently, that is in n log n time versus quadratic time. Because if we have a computational process that takes quadratic time, then it's not going to scale. We're not going to be able to do large numbers of particles. Simulations of the real world, usually we wind up doing huge amounts of data, and we cannot have a quadratic algorithm. And this is just first indication of that, of why if you want to do this simulation, you better know about some data structure like priority queues. If you try to do it without it, you're not going to be successful. All right, so let's take a look at what happens. There's a number of things that you might consider trying. One idea is a so-called time-driven simulation. And we just say we're going to update everything every dt seconds. And then we go ahead and do that, and then we could check if there's a collision, if the two balls, some pieces of two balls are occupying the same space. And if there is, then we could roll back time just a little bit and try to figure out exactly the moment at which they collided, and then figure out how their position of velocity should change accordingly, and then continue the simulation. But this has a huge problem. The first one is that you have to check all pairs of balls for overlap. So that's quadratic. So it's going to be really a lot of overlap checks. You're not going to be able to do it for a huge value of n. But the other thing is, even if n is small, if you do a very small dt, then you're just doing this calculation over and over again, and there's just too much computation, moving the balls a little bit at a time. On the other hand, if you try and improve things by making dt too large, you might completely miss a collision, as shown in the example at right. So figuring out the value of dt that would really work is a huge problem for the time-driven simulation. Instead, what we want to do is called an event driven simulation. And this is a very general concept that's useful in all kinds of contexts. And we're only going to change things when something happens. So since the only thing that matters is collisions, we're going to figure that particles move in a straight line between collisions. And what we're going to do is focus only on the times when the collisions are going to occur. And so the way we're going to do that is to maintain a priority queue. And that priority queue is going to have all the possible collisions that could happen in the future, and they're going to be prioritized by time. And when we remove the minimum element from the priority queue, that's the next collision that we have to deal with. And so we have two phases. We have prediction and resolution. So at some time, t, we can take two particles. We know their position and velocity is shown at the bottom here. And we can predict exactly the moment at which they'll collide, assuming that something else doesn't happen to them in between. And then, so then we'll put that predicted collision time on the priority queue. Then later on, when that time comes to pass, we'll be right at the moment when they collide, and we can figure out what to do. Now, there is the possibility that something else happened to them in between, and we'll talk about that change too. So we have to do collision prediction, which is given position, velocity, and radius, when's it going to hit with another particle or the wall. And then there's resolution, which is to figure out how to change the velocities of the particles according to physical laws. Now, this part I'm not going to talk about in that much detail right now because it's high school physics. And so I think most students have had some high school physics and will be able to do this math or at least be convinced that the code that does this math is correct. So if you know that you have a particle that's at a certain position, Rx, Ry, and it's got a certain velocity, Vx in the x direction, Vy in the y direction, then you can, from the distance to the vertical wall, you can figure out how many seconds it's going to take until it hits it. It's basically that distance divided by the velocity. And so that's the prediction. And then the resolution, when it hits the wall, is just going to change the velocity. So that's you know what the position is. So that's just an example of collision prediction. When's it going to hit the wall? And resolution, what do you do when it gets to the wall? When you have two particles, there's definitely more math. And again, this is high school physics, and we're not going to test on it or even go through the details. But it's just a little bit of arithmetic with the velocities and the positions to deal with what happens how to predict when a given particle is going to collide with another given particle, knowing their velocity and position. So you have to take both velocities and divide their distance by those and so forth. So there's simple formulas to tell us what to do. And we can also figure out the formulas for what we do once they do collide. And again, nobody's claiming that this is easy, but this is the physics part. And it's worked out, and it comes from Newton's second law. And anybody taking high school physics will be able to deal with these formulas. And the rest of us may have to go to our reference book to get up to speed on them. But once it's reduced to code, we can it might have some trouble debugging at first, but at least we can be convinced that it works. But now let's look at the computer science code. So this is just extending our ball data type that we use for the bouncing balls that didn't collide to taking into account these extra things. So ours will have mass, so there'll be some big heavy ones that make things more interesting. And there's also a variable called count, which is the number of collisions the particle's been involved in, and that's useful for a couple of purposes. So we're going to need a bunch of procedures which do the prediction and the collision resolution. Given a particle, what's the time till we hit that particle? What's the time till we hit a vertical or horizontal wall? And the same thing is if we're at the point where we're hitting a particle, what do we do? Same with vertical and horizontal wall. So that's the skeleton. We need those procedures that implement those physics rules for every particle. And this is what they look like. And again, this is high school physics, so we're not going to do it in detail, other than to point out it's really not a huge amount of code. Lots of dx's and dy's and dv's, but really not a huge amount of code. And the other point is we're going to return infinity if there's no collision at all. So that is going to keep that on the priority queue, that event on the priority queue forever. Okay, so that's the procedures that we need, and then there's similar ones for the horizontal and vertical walls. Okay, so now let's look at the main loop for the event-driven simulation. So the first thing is we're going to, for every particle, we're going to compute the next time that it might hit every horizontal and vertical wall. Well, actually, if it's going away from a wall, it's not going to hit it, so that would be infinity. But if it's going towards a wall, then we'll compute the time, and then that's a time in the future. We'll put that event on the priority queue with that time as the key. And then we'll do the same thing for all pairs of particles. So we do have a quadratic initialization phase that we perform just once to get the priority queue filled up. Now, all collisions might not happen. So we might have two particles that are on a collision course, and we're going to predict that point for both of those particles, even right at the beginning. But it might be the case that there's a third particle that knocks one of those out before that thing happens, and that event would be invalidated. So the simulation has to be careful to take that into account, but that's not difficult to do. So here's what the main loop is. So we're going to take the next event from the priority queue. That's the next collision that's going to happen. From all our calculations, there's one collision that's going to happen next. Then we test whether that event has been invalidated. And we do that by using that count field in the particle. So then that tells us what time it's going to be next. So then we have to go through all the particles and change their positions on a straight line trajectory. Where would there be after that much time? Then we have to take the two particles that collide and change their velocities. They bounce off one another. Now those two particles' velocities have changed. Essentially that invalidates the future collisions involving those. And then what we have to do is for those two particles is go through and predict the future collisions with any walls and collisions with any other particles and put all those new events onto the priority queue. But that's it. You got two particles, change their velocities, figure out the future collisions of those particles with the wall, and update the priority queue. And then the main loop is take the next thing off the priority queue and keep going. That's the code that we'll look at next. So we have a bunch of convections just to reduce the code. And if we have this thing called event, which involves, it says between two particles something is going to happen at a certain time. And we're going to adopt the conventions that if neither particle is null, then we're talking about two particles. If one of the particles is null, then we're talking about a wall, a vertical or horizontal wall. And if both particles are null, we're saying we just want to redraw things. That's a bit of a hack, but it cuts down a lot of code. Our compare to is by time. And then, again, we need an is valid to check about intervening collision. And then here's the skeleton of what's going to happen with the collision system, which is the key thing is this prediction method that takes a particle as argument and adds to the priority queue all the possible collisions involving this particle. So it's going to go through every particle and call the time to hit method for that particle, and then it'll put an event on the priority queue for that time, this particle with that particle. And then it'll also put an event for the vertical wall and the horizontal wall, again using this null convention to say that the event second argument null is vertical, first argument null is horizontal. So that's a key method that gets used in the simulation for each of the two particles that are going to collide. So now we can look finally at the main event-driven simulation loop. There's build the priority queue. There's do this prediction for every one of the particles. And then also we're going to put as the first thing to happen always an event that says redraw everything. That's just a way of making sure that the simulation keeps proceeding. It's an easy way to get things drawn. Okay, so now the main loop is while the priority queue is not empty, we're going to pull off an event. We're going to test whether it's valid, and that's to just check if anything happened with those two particles. We're going to pull off the two particles, and then we're going to move all particles by the amount of time that has elapsed since the last event. And then we're going to test which of the four types of events that it is. It's either redraw, bounce B off A, or bounce off a vertical wall or horizontal wall. And then we'll go ahead and do the predictions of each of those particles, A and B, against all other particles. That's pretty much all the code for the simulation. This is data-driven code. One thing we can do is just run it for 100 balls in random position at random velocity. But what's nice about data-driven code is now that the code's working, and again, we're not saying this is trivial code to write, but it's definitely manageable, and it's enabled by priority queues. Without priority queues, it would be quite a bit more complicated to figure out how to do this, and also it wouldn't be reasonably efficient at all for large data sets. So that's a simple simulation, just generate random positions. People might be interested in this one. Now, this isn't exactly precisely what would happen in the real world, mainly because we didn't put in the simulation what happens when three particles are touching, or there's two touching and another one hits them. And also, nobody racks up a set of billiard balls such that all 15 are touching in all places. So life can be complicated when you're trying to simulate the natural world. This is a little bit about Einstein's experiment. If you got one big particle like a pollen grain and lots of little particles like atoms and molecules bouncing against it, the big one is going to move about randomly. Then this is another famous physics experiment showing diffusion. There's many other things that you can do with this basic collision system. If you have huge numbers of particles and you measure the number that hit the sides and the frequency with which they hit the sides, you can do experiments relating temperature and pressure and many other things, or do three-dimensional versions. Again, simulation of the natural world is an increasingly important application of computing. And you need efficient data structures like priority queues to get it done.